let's take some time now and talk about 6.9, which is curve fitting with polynomial models, right? We've done curve fitting with linear, we've done curve fitting with quadratic, and now we're talking about how we can model data using different polynomial functions. So what I want you to be keeping in mind is what are two different methods that can be used to determine which polynomial best represents a given data set? And then I want you to be able to describe both. Okay, there's two ways we can figure it out. So let's take a look at the first way. The first way is called using finite differences. And a finite difference is a difference between pairs of y values for evenly spaced x values. Okay, we're going to look at how this works. But as we calculate finite differences, we'll start to see a pattern. If the first finite difference is constant, we are looking at a linear function. If the second finite difference is constant, it's quadratic. If it's the third, it's cubic. Notice how the degree matches the level that we're on. Okay, so let's look at how this actually works, because I feel like we need to see it in action to really understand it. So here's our first example. Here's a data set. It represents the order pairs 12, negative 30, 15, 15, 18, 30, 21, 34, 24, 41, 27, 60. Okay, we can represent this as a polynomial. So what we're going to do is we're going to calculate the finite differences. The first one we're going to do is the first finite difference. And to do that, we're just going to subtract the y values, right? It's the difference in pairs of y values. So I'm going to do 15 minus negative 30. 30 minus 15. 34 minus 30. 41 minus 34. 60 minus 41. And when we do that, 15 minus negative 30 is 45. 30 minus 15. Notice I'm always taking the second one and subtracting the first one. Is 15. 34 minus 30 is 4, 41 minus 34 is 7, and 60 minus 41 is 19. So our first level of finite differences is 45, 15, 4, 7, and 19. That doesn't tell us anything. It doesn't get us any closer to any data, so we're going to go to the second level. 15 minus 45 is negative 30. 4 minus 15 is negative 11. 7 minus 4 is 3. 19 minus 7 is 12. Second level, this would be, if these were all the same, we'd have a quadratic. We don't. These aren't all the same, so we go to the third level. Negative 11 minus negative 30 is 19. 3 minus negative 11 is 14. 12 minus 3 is 9. Not all the same, so it's not cubic. Fourth one, 14 minus 9 is negative 5. 9 minus 14 is negative 5. Because these two negative 5s are the same, we have a fourth, which means this data set can be well represented with a quartic function, a degree 4 function. Okay? Now I'm going to show you a second one. In this second one, we're comparing years and populations. So this one's a little bit different. Okay? Notice the years are evenly spaced. We calculate every 10 years, and then we have all sorts of populations. So let's calculate the first finite difference. 4011 minus 2853 is 1158. 5065 minus 4011 is 1054. 6720 minus 5065 is, and you can see all these first differences. This one minus this one cranks out that one. 5065 minus 4011 cranks out 1054. Not all the same. So we go to the second one. Definitely, again, not all the same. But we go to the third one. At this third level, you'll start to see that 705, 728, and 742, those are pretty darn close. They're definitely a lot closer than these, and if you look at your data, we're 3,000 away up here, and down here we're only 14 away. In the grand scheme of things, 14 away is pretty good. Okay, and here we're 23 away. Still pretty good. Especially like right here, look at some of these big differences up at the top. Okay, compared to these little differences down here. And so what we can say is for the second example, the third differences are close. So a cubic polynomial is a good option to use for modeling this data, right? We're going to say cubic because we get pretty darn close. We didn't hit exact like we did over here, but we got pretty darn close. So we're going to use a cubic. So calculating the finite differences, right, first, second, third, fourth, that will tell us which polynomial or which type of function is a good match for our data. Right here, it was a quartic function. That was a good match for our data. Here it was a cubic function. That was a good match for our data. Okay, so speaking of matching our data, let's talk about how we would do that. Let's model this data as a cubic function. Okay, so I'm going to say, okay, I'm going to plug in my data into the list, right? You all know how to get to stat and edit the list. And so you're going to plug in all your years, and you're going to plug in all of your populations. Then we said that if you throw back, a cubic polynomial would be a good option. And since a cubic polynomial would be a good option, we're going to use cubic regression. So we go stat, calc, and we use cubic reg. Then we're going to do it for L1 and L2, right? L1, L2. If we want to save the equation, remember we type in one more comma and then input y1. If you want to remember how to do that, I'd be happy to show you. Okay? So notice this function is a cubic function, ax to the third plus bx squared plus cx plus d. Okay? Then we have a, so that tells us what our leading coefficient is. We have b, that tells us what the coefficient on the x squared is. We have c, and we have d. Now this one gets a little out of control, okay? But it's the same information there. Now, this very last thing, r squared, remember, this tells us how well our data matches this cubic equation. This cubic equation is not perfect, although this r squared here tells us it's pretty darn close, right? It's the correlation coefficient, how well the data matches the equation. Now, what we did here, I'll throw back again, we calculated all the differences, we picked the third, or the cubic polynomial, and then we found out what the equation of that cubic polynomial would be. Okay? And so since we did that, we were able to write this equation, and we could model all this data as an actual equation that we could graph, we could plug values into, we could have so much fun with, right? So much fun with. Okay, there's another way to do it, because in some real-world examples, we can't just rely on second differences. For example, let's look at this one. The table shows the opening value of a stock index on the first day of trading. Okay? So if you look at this, remember, for finite differences, we said it has to be a case where we have evenly spaced x values. Now, here we're talking our x values are a year. These aren't evenly spaced. 1 year, 1 year, 1 year, 3 years, 1 year, 2 year, 1 year. These aren't evenly spaced. So finite differences really aren't going to work well for us. But what we can do is we can plug into our calculator and try some different regressions and then see which one is the best fit, right? Because r squared tells us how well our data fits. And so looking at the r squared will help us figure out which equation is best here. Here's what I mean. First of all, you're going to have to plug everything in. And when you input this data into lists, you're going to want to think about this year in terms of how far away am I from 1994. Well, here I'm 0 years from 1994. Here I'm 1 year, 2, 3, 6, 7, 9, and 10. And I want to think about how far I am from 1994. It's going to be a little bit easier for us to work with rather than trying to say, okay, I'm going to plug in 1994 as my x value. No, that's not going to give us a good look. Okay, so anyway, sorry. Then let's try cubic regression on these two lists, L1, L2. Notice, for cubic regression, my r squared is 0.6278 and so on. Okay, that's not a great r squared value. It's average. I mean, it's like a D. We could give this r squared a D. I mean, it didn't fail, but it's not great. Can we do better with something else? Let's try quartic regression. Look at our r squared here. Our r squared did better. Here we got more of like a B. It's a better r squared for us, which means this quartic regression is a better option for our data. Okay? Because r squared is closer to 1 for quartic regression, we're going to use this equation to model the data. So now as you're looking at this, obviously normally it should be ax to the fourth plus b and so on. A you would have to scroll up to get to. Okay? But we could have all the information to write the equation. So at the very beginning, I asked you this. What are two different methods that can be used to determine which polynomial best represents? Okay. What are the two methods we talked about? The first one, easy, finite differences. Crank them out. Which one is constant? Which one is equal? Here was the fourth. Here was the third. And so that told us, hey, I'm going to use cubic. And that's great for when we have an opportunity to calculate those finite differences. But we said that wasn't always going to work very well. And so sometimes we're going to have to compare the r-squared values. So we can either use finite differences or we can use r-squared to decide which one really represents it best. Okay, so I'm giving you two choices. Finite differences are great, but also rely on r-squared in some cases too. Okay? Those two will help you figure out which equation works best. Once you know which equation works best, then you go to regression to write the actual, what it actually is. Okay, so finite differences, r-squared, kind of guide you to where you need to get. This regression function will give you the final answer. Okay? Make it happen, people. You can do it.